quick line. Start of a play.
All right, so like I mentioned before, thank you. So far our tests have been for series with positive terms. We've always said that our terms, a sub n, b sub n, greater than 0. Here we're talking about series with both positive and negative terms. And when we talk about alternating series, we're talking about strictly alternating series. So every other term is a different sign. But we'll talk about how we can extend one of the ideas we talk about to series that are not strictly alternating. So for alternating series, we have a nice test, the alternating series test. So I'm going to say the way that our book does it, it says that a sub n is greater than 0, and then we just use a -1 to the n or a -1 to the n plus 1 to give us an alternating piece. So the term, the a sub n that we're talking about is the positive part. So we're going to say these two series, the sum n equals 1 to infinity, -1 to the n, a sub n, and we'll have -1 to the n plus 1, a sub n. So we either have even terms or odd terms with a negative sign. These two are going to converge under two conditions. And both the conditions have to be true for us to have convergence. One, we need the limit as n approaches infinity of a sub n to be 0. So this is just our nth term test for divergence. If that limit isn't 0, then our sequence can't converge. And the second one is a sub n plus 1 has to be less than or equal to a sub n for all n. And I'm going to make a little note here. We can delete the first a finite number of terms, and our alternating series test will still hold. So I'm going to say first capital N terms, and this test will still hold. So if our sequence, it grows and then eventually it's decreasing, then we're okay. Yeah.
Is that less than or equal to in magnitude?
Well, the a sub n is just the magnitude part.
Oh.
So the -1 to n is what gives us the alternating sign. So we're saying that we're just interested in the part that tells us the magnitude, like you said. And so what this is going to guarantee that our sequence is decreasing, and our limit, we get the test ensures us that our sequence of partial sums is bounded and monotonic. Is essentially what this is doing for us. All right, so I just want to look at a couple of quick examples. This is a part where we sometimes have to be careful to show that our sequence is strictly decreasing. Sometimes it's not easy to see. So I'm going to say we're going to test n equals 1 to infinity of -1 to the n plus 1 over 2n minus 1. And I'm going to write out a few terms here. 1 minus 1/3 plus 1/5 minus 1/7 plus dot, dot, dot. All right, so the limit as n approaches infinity. I don't need to worry about this. We're just worried about the magnitude of 1 over 2n minus 1 is 0. So we're good on that part of the test. And I'm going to say a sub n is 1 over 2n minus 1, and a sub n plus 1 is 1 over 2n plus 1 minus 1, which is 1 over 2n plus 1. And for this, I would say it's pretty clear that 1 over 2n plus 1 is always less than 1 over 2n minus 1 for n greater than or equal to 1. So a sub n plus 1 is less than or equal to a sub n for n greater than or equal to 1. So we're good there. So the series converges. So that one's not too bad. Alternating series test one is nice like this. It's quick and easy to apply. Yeah.
You can only use this to determine convergence, right? Not divergence. So like if it doesn't work, can you say the divergence or?
Well, if the n limit as n approaches infinity, the nth term is not 0, then you can say divergence.
Well, what about the second term?
The second one, so both have to be true for the sequence to converge. So if either one doesn't hold, then the sequence does not converge.
And divergence.
Right.
So this does demonstrate divergence.
What's that?
If it fails this test.
Right. Let's look at another example. Slightly different. Sum n equals 1 to infinity of minus 1 to the n over 2n minus 1. So this is 1 minus 2/3 plus 3/5 minus 4/7 plus dot dot dot. And let's pretend that we didn't do this test, our limit as n approaches infinity. We did not do that test first. We wanted to do the test to see if our terms are decreasing. Because what is the limit as n approaches infinity of this thing? 1/2. So that if we tested that first, we would know that this diverges. So let's pretend that we didn't test that. So I'm going to say a sub n. We're going to check to see if our sequence is decreasing. A sub n is n over 2n minus 1, and a sub n plus 1 is n plus 1 over 2n plus 1. So the denominator is the same as we got there. Now I would say it's not immediately apparent that a sub n plus 1 is always less than a sub n. You can't just look at that and say, oh yeah, that's always less. It's not, I would say it's not easy to see that just by inspection. So let's see how we would have to show that. So we're going to say n plus 1 to n plus 1. I'm going to say less than or equal to with a question mark. N over 2n minus 1. If so, then n plus 1 over 2n plus 1 minus n over 2n minus 1 has to be less than or equal to 0. Now we can't work across this inequality here because we don't know if that inequality holds. So what we have to do is work with this and show that it's less than 0. So we're going to find a common denominator and simplify this out a little bit. So we're testing, we're working with this to see if it's less than 0. So I'm going to do, I get an n plus 1 times a 2n minus 1 minus n times 2n plus 1 all over this common denominator of 2n plus 1, 2n minus 1. Well, this equals 2n squared plus n minus 1 minus 2n squared plus n all over that denominator. And this I get a 2n squared minus 2n squared, n minus n. I'm just left with negative 1. And for n greater than or equal to 1, this denominator is always going to be positive. So this is less than 0. So that's how we would show that this sequence is decreasing. Yeah.
Can we still use the derivative technique to demonstrate decreasing of these?
Yes. All right, but we know this one diverges because a limit as n approaches infinity of a sub n is 1/2, which is not 0, so it diverges. So it's a decreasing sequence, but it doesn't converge. All right, questions so far? All right, I want to take a look at a couple of sequences. And these are ones that I think that we're familiar with already. So I want to look at the sum, n equals 1 to infinity, of minus 1 to the n over n. This is the alternating harmonic series. We know that the limit as n approaches infinity, this is pretty easy to see, 1 over n is 0. So we're good there. And 1 over n plus 1 is less than or equal to 1 over n for n greater than or equal to 1. That's easy to see. This denominator is bigger, so that number is smaller. So this series converges. But the sum n equals 1 to infinity of the absolute value of minus 1 to the n over n, which is the harmonic series, diverges. We call this situation conditional convergence. The alternating series converges, but the absolute value of that alternating series diverges. So we call that conditional convergence. Now I want to look at the sum n equals 1 to infinity of minus 1 to the n over n squared. And it's easy to see. Limit as n approaches infinity of 1 over n squared equals 0, and that 1 over n plus 1 squared is less than or equal to 1 over n for n greater than or equal to 1. That's easy to see. So that series converges. The alternating series converges. And the sum n equals 1 to infinity of the absolute value of that series is just the sum n equals 1 to infinity of 1 over n squared. And what kind of series is that? That's a convergent p-series. So we call this series absolutely convergent. So the alternating series converges and the absolute value series converges. So let me make those definitions a little more formal. So interesting things happen when we get conditional convergence. Absolute value, absolute convergence is nice because it gives us another tool to work with. So we're going to say our definitions. Just so we're make this clear. And I'm going to say here a sub n can be positive or negative. So here I'm letting the sign change with the entire term. So we're going to say that the sum a sub n is absolutely convergent. If the sum of the absolute value of each term converges. And we're talking about an infinite sum here. And a sub n is conditionally convergent. If the series with positive and negative terms converges. But the absolute value series diverges. So we would say the alternating harmonic series is conditionally convergent. And the nice thing about absolutely convergent series is absolute convergence implies convergence. And what that means in symbols is that if the sum of our absolute value series converges, then the alternating series or the series with changing signs also converges. And the way, just an outline of how we would see this is we can, if we do direct comparison between this series, we need to do a little work, and this series, we can get the convergence of the alternating series by direct comparison with something that's related to the absolute value series. Because if you kind of think of it intuitively, if our signs are changing, positive and negative, the sum is going to be less than if we keep all the signs, keep all of our terms positive. So we get kind of a direct comparison thing happening there. There are a few more steps than that, but that's the gist of it. And this is nice because absolute convergence lets us work with series that do not necessarily strictly alternate. So our alternating series test, we have that -1 to the n or the -1 to the n+1. So we have to have strictly alternating terms. Absolute convergence lets us work with series that don't strictly alternate. So let's look at an example of that. Oh, and I want to note here, we can't conclude the converse. The sum of a sub n converging does not imply that the absolute value series converges. And our counterexample there would be the alternating harmonic series. Alternating harmonic series converges, but the absolute value series does not. Any conditionally convergent series would be the counterexample to this. So this only works one direction. You have absolute value series converging, then the alternating series converges. All right, so let's look at an example of this, and then I want to show you an interesting thing that happens with conditionally convergent series. So if we had something like this, sum n equals 1 to infinity of sine n over n squared. So this is sine of 1 plus sine of 2 over 4 plus sine of 3 over 9 plus dot, dot, dot. We get positive and negative terms because we know that the sine function is periodic. It varies between positive 1 and negative 1. But it's not necessarily every other term. So we might have some positive and some negative and some positive and some negative and some positive and some negative. But it's not every other term. So this is not strictly alternating. So we can't apply our alternating series test. Alternating series test only applies to strictly alternating series. But let's look, we say a sub n is sine of n over n squared. What can we do here? Absolute value of a sub n is less than or equal to what can I compare this with? What's the largest that sine of n ever gets? 1. So this is less than or equal to 1 over n squared. So when I take the absolute value, this is going to be between negative 1 and 1. And I'm going to say since the absolute value of sine n is less than or equal to 1. And what kind of series is this? That's a convergent P series. So our original series converges. So there were a couple of mathematicians, and they were working with series, and one mathematician said to the other, "Do you realize that if we make all the terms of this series positive, it still converges?" And the other mathematician said, "Absolutely." That was a bonus. All right, so this is nice because we used absolute convergence and we used direct comparison. It's always nice when you can use direct comparison. That's what I think. All right, questions? All right, let me show you an interesting thing, an interesting property of conditionally convergent series. This is kind of an extension topic.
We need to know this.
Well, need is a very subjective term.
On the test?
It will not be a question that I would ask about as a test question, but it might be a good topic to know something about on the test. I'll put it that way.
So it might help you to do a hard test question.
So you might be able to avoid doing work by using some sort of trick.
Conditionally convergent series can be rearranged to produce any sum. So you can show that if you rearrange the terms of a conditionally convergent series, you can produce any sum that you want. So for example, I just want to show you one. N equals 1 to infinity of minus 1 to n plus 1 of 1 over n. Now we can show, I think this comes out a little later, that this is when we talk about a power series for the natural log function. So this is 1 over 1 minus 1/2 plus 1/3 minus 1/4. And if we keep going, that equals the natural log of 2. If we write out a power series for the natural log function, so that quantity equals the natural log of 2. I'm going to rearrange this. So I'm going to put some negative terms and then some positive terms together. So I'm going to rearrange to 1 minus 1/2 minus 1/4 plus 1/3 minus 1/6 minus 1/8. So our even terms are negative and our odd terms are positive. Plus 1/5 minus 1/10 minus 1/12 plus 1/7. I'm going to just write out one more. Minus 1/14 minus dot dot dot. And now I'm going to gather these together. 1 minus 1/2 minus 1/4 plus 1/3 minus 1/6 minus 1/8 plus 1/5 minus 1/10. This should be 12, right? Minus 1/12 plus 1/7 minus 1/14. There we go. Well, 1 minus 1/2 is 1/2 minus 1/4. 1/3 minus 1/6 is 1/6 minus 1/8. 1/5 minus 1/10 is 1/10 minus 1/12. This is 1/14. And this is 1/2 of 1 minus 1/2 plus 1/3 minus 1/4, which is half of what we started with. So you can prove, and there's an article in your it references an article in your book on page 624 that talks about this topic. Gives a good explanation. You can prove, it can be proven that you can rearrange this sum to be any quantity. You choose a quantity you want, and you can rearrange that sum to be any quantity. So when we have a conditionally convergent series, an infinite conditionally convergent series, you can't rearrange the sum to reach any conclusion. You can rearrange a finite sum, but if you rearrange an infinite sum, then you end up in some murky water. So it's just kind of an interesting property of conditionally convergent series. Yes?
So if we have some sort of like geometric or other series that we do have tools to find the sum of, if we can demonstrate that it's conditionally convergent, we can just say you can't do that because you can just reorder the terms and do this.
Right. So you can't. So we can show that this sum is a natural log of 2 because we come up with a power series expansion for a natural log function. You can't start rearranging the terms because then things go haywire. So it has to be in exactly this order, and you have to leave it there and not touch it. You can't mess with it. Yeah. All right.
So I better answer this question.
That's not what happened. Oh no.
All right, there we go.